ESE. Aluminium. Let me see. First of all, well, in a galvanic cell, all the processes there, the redox processes, happen spontaneous. So by nature, from the energy potential, for the redox potential point of view, they work by themselves. That means by themselves. Without adding energy, without pushing the process in any other direction. That is the way how it works. And the fact or the reason for that is because the redox potential are in a level that it works by itself. And the electrolysis is now the opposite direction. So redox process can be forced in another direction. By supplying energy or mostly electrical work. Yeah? Because the redox process, it is a, well, at the end, a shift of electrons in the one or in the other direction. One direction, it goes by itself. If you want to have them moving in the other direction, you need a power, an electrical work to push them into the other direction. And that is done in an electrolyzer. So I have to turn my paper because now I will do it. Sorry. In a bigger scale. And we will divide our paper into parts. On the left, we have the galvanic cell. And on the right, we have the electrolysis. So we have, in both cases, we have a big beaker. And the beaker even is divided in two parts. The division is done by a so-called permeable porous membrane. These permeable membrane allows one part of ions or particles to pass. Not all. And on the left side, we have the zinc system. Where we have the zinc electrode, which we know already, in a solution of zinc sulfate. So this is elementary zinc electrode. And we have in there the solution of zinc sulfate. So in there, automatically we have SO4 2 minus ions. And we have zinc 2 plus ions from the zinc sulfate. On the right side, we have the copper system. So a copper electrode made out of pure copper in a copper sulfate solution. That is pure copper. And in here we have the copper sulfate. So copper 2 plus ions and even SO4 2 minus. And what we are doing now is we connect those two electrodes via electrical connection. So here we have the opportunity to measure the potential between those two electrodes. A voltmeter, where we can measure the potential which is built between those two systems. So when we look to that, what will happen? We already had it in the Daniel element. So what are you expecting when we have a system like this? We will have a current, so we will have a redox potential. And what will be the process in here? What will happen in the zinc system? Well, the zinc is the less noble metal compared to copper. What happens? No. Again, so first of all, what happens here? What will be the process in this system? Sorry? Salt, what? Salt bridge. There is no salt bridge. We have a permeable membrane now. So here, sulfate ions can pass. But what happens here in that system? What's the initial process? When you connect zinc with copper electrode, and in both systems you have the ions of the metals. So what happens on the left side? We just talked about. So the zinc will be oxidized. So you will have the formation of additional zinc 2 plus. And the zinc electrode will get porous, or by time smaller and smaller. because the zinc metal is oxidized to formate zinc 2 plus ions. The concentration of zinc 2 plus in the left system is increasing. And on the other side, we will have the formation of additional elementary copper. So the copper electrode will grow, get more heavy. We will have more elementary copper because the copper 2 plus now will be reduced to form additional elementary copper. And that could work because the electrons, by the oxidation of zinc to zinc 2 plus, electrons are released, and these electrons, they can now move via the electrical wiring to the right side where we have the copper electrode, and here those electrodes can be used to reduce copper 2 plus to form additional elementary copper. So these are the electrons which move from the left side to the right side. For the balancing of the charges, now sulfate ions can move from the right side to the left side for the balancing of the charges. Because here we take away electrons and we have more zinc 2 plus. And here we take away the copper ions and formate copper. So we have less positive charges after a while. So when electrons move here to the right, the negative charges of the sulfate ions can move through the membrane from the right to the left. So this membrane is permeable for the sulfate ions. And that is how it works by itself. What we can measure is the redox potential, delta E. That is what we already know, 1.10 volt. That is what we can measure. So the process will be copper 2 plus 2 electrons coming from the zinc system will form elementary copper. And the electrons come from the zinc, which is oxidized to form zinc 2 plus 2 electrons. And these are the electrons which can move. Those are the electrons which we see moving here, and we can measure the redox potential, the delta of those potentials, and we know it's 1.1 volt. So we have a couple of zinc 2 plus, and copper 2 plus. Copper is reduced, zinc is oxidized. And that is the direction which naturally works. Works by itself. We don't have to add some energy because the redox potentials show us zinc will be oxidized, copper reduced. Now, in the electrolysis, we force the system to work in the opposite direction. So here we have our beaker again. We need a little bit more space on the top. We have the semi-permeable membrane again, to divide it in two parts. We have on the left side our zinc system as we know it. In the zinc sulfate solution. On the right side, we have the copper system as we know it. So that is nothing new. In the copper electrode in a copper sulfate solution. And now we do not have this system working by itself. We have to add power. Sorry? Electricity, yeah. We have to add electrical work. So we have to connect it with an external power source to push the electron movement in an opposite direction. So now we have here an external power source where we have the negative part here, the positive part here. So now we push electrons to move from the right to the left side. This power source, that's the power source. You can connect it to your socket, where we have electrical power. And now we operate the system that electrons come from the copper side to the zinc side. In this case, we will have the formation of additional zinc. And the copper electrode will dissolve by time. So copper ions are produced. Here we will have the copper 2+ production and the zinc 2+ ions from the solution will be reduced to form elementary zinc. So it's exactly the opposite. But that only works when I add power. What do you think is the minimum of power I have to invest of potential? 1.1 volt, but in the other direction. So here exactly we need 1.1 volts. To push it in the other direction. And that is what we call electrolysis. By applying DC voltage. And this is the 1.1 volt. The inversion of the reaction occurs. So here now we have the reduction of zinc to form elementary zinc. And we have the oxidation of copper. Huh? But that means the invest of power. So when we look to the system, the overall system, we can say we have zinc 2 plus and copper. And we have here copper 2 plus and zinc. So what are you expecting when you are not investing any power from outside? It will work from the right to the left side in this case, because zinc will be oxidized and copper will be reduced, the copper 2 plus. So this is the direction which works by nature, or in the Daniel element in the galvanic cell. And if you are interested in the opposite direction, you have to add electrical power, enforcing by electrical power. Enforcing by investing electrical power. And this is the electrolysis. Well, in reality, there is sometimes you have to add a little more than these 1.1 volt to start the system work. And that is what we call the decomposition voltage. So the minimum in the difference of the redox potential in the opposite direction, because you have here on the surface of the electrodes, you have some processes where you have to add a little more power than theoretically needed to start the electrolysis. So here we can produce electrical power out of chemicals. If we want to bring back the chemicals in the initial form, we have to invest power. Here we just have a system out of zinc and zinc 2 plus copper and copper 2 plus. And then when we design it like here, we can create electrical power. If we'd like to recycle our chemicals in the way that they can be used again to produce electrical power, we have to add power from outside. Do you know a system where we use that daily? In batteries. So in the mobiles, every day, or I don't know, every 2-3 days, you have to charge them. There is we call it accumulator. The difference between a battery and an accumulator is normally the battery only works once, and then you have to throw away the battery. It's not reversible. In the accumulator, it is reversible. So you can operate it like here to invest power from outside. Then you have the system in a way of chemicals at the end, which work by itself to produce electrical power. Then you can use your mobile, your laptop, your whatever, electrical car. But from time to time, you have to recharge it. And this is a reversible process, not for all systems, but of course in the accumulator, it is reversible. So accumulators are galvanic elements in which the process takes place during the current consumption, discharge, and can be reversed by applying electrical energy from outside, which we call charging. So first of all, galvanic cells are energy converters. Which chemical energy is converted directly into electrical energy? So this is, at the end, we call them batteries. Most application for example, batteries. Accumulators are galvanic elements in which the process taking place during the current consumption is discharge. We call it discharge. Discharging can be reversed. By adding electrical energy. From another source. And this is what we call charging. So now you can imagine for batteries, for accumulators, there are quite a lot of systems in theory we can develop. We always just have to look to the redox table of elements. And then we see, okay, that system might work by itself in this direction. We can use it in the battery operation mode. And if it is reversible, then we can charge it and use it as an accumulator. Do you know the most common battery systems? What is it? Lithium ion, yes, that's an accumulator because we can recharge it. And that is quite a complex system, the lithium ion. You know, lithium, okay, normally it will be oxidized because lithium is not very noble. It is in the alkali elements in the first column of the periodic table. So very ignoble, it will be oxidized by itself. If you want to produce lithium, you have to add energy from outside. But it is more complex. In the lithium ion battery, lithium iron phosphate, there are different systems, but they are the most efficient, which we know up to now. The lithium ion technologies, you will find that in cars nowadays, in electrical cars, in e-mobiles. Do you know other systems? The lead acid battery, that is the one which is used normally to start a car. Even a fossil engine car, you need to start it. Therefore, you need electrical power. And this is the lead acid battery. Lead is not so fine because it's a heavy metal. So in the point of sustainability, it's poisoning, so you should not throw away the lead acid battery in nature. You have to bring it back for recycling. But that is a very stable system, well developed over 100 years, and the most common starting battery in the cars. So let's have a look to the lead acid battery. So even here we have one electrode is out of elementary lead, the symbol PB. So we have a lead electrode, and the other electrode is a lead oxide electrode, in this case PbO2 electrode. What is the oxidation number of lead in elementary lead here in the pure lead electrode? 0. And here in the lead oxide, +4. So we have 2 oxidation states for the lead. The electrolyte, that is the solution, we call it electrolyte, where the electrons are in. And in the lead acid battery, what do you know? Do you know what acid is it? Yeah, it is H2SO4, 20%. So it's a very strong acid, and even in a high concentration, don't dip your fingers in. So it's an acid solution. We call it electrolyte. The system looks like that. We have our container where the solution, the acid is in, and the electrodes are dipped in. And we have the semi-permeable membrane. So one here in between, we have the membrane, as we already know it, permeable for the sulfate ions. And we have on the left side the pure lead electrode. And we have on the right side the lead oxide, but it's a coating of a lead with lead oxide. So we have the lead in between and coated by lead oxide. And the solution where they are in is the sulfuric acid, 20%. And this is the permeable membrane in between. So what happens? What do you think? What will be oxidized? So the elementary lead, Pb, will be oxidized, but in this case, it will form lead 2 plus sulfate. Huh? So here we have the sulfate ions in the system, and it forms the lead sulfate. And 2 electrons. That's the oxidation. And what will be reduced? The PbO. So we have the lead oxide, and even here we will have the formation of PbSO4, and we come here from +4, and here what's the oxidation number in here? It's +2. +2. Here it is 0. We have here the uptake of 2 electrons. And of course, we have the sulfate even here, SO4 2-. So we are in a very acidic environment. No, you can't see. We are in a very acidic environment. Now let's check. First of all, charges are, or electrons are fine. We have +4 to +2, 2 electrons. But now when we look to the charges, we have 4 negative charges on the left side and no charge on the right. And we are in an acidic environment. What do you think? Do we have to add? Sorry? Not hydrogen. We have to balance the charges. So what do we have to? Alkali. In an acidic environment, we don't have it. So what do we have? In an acidic environment, what do we have? So protons, or H3O plus. How many do we need on the left side to have 0 charges on the left? How many H3O plus do we need on the left to equalize all the negative charges? We have 4 negative charges. How many H3O plus do we need? Hey, you are really great. +4 H3O plus. Then we're done with all the charges because we have no charge on the right. And now 2 for negative, for positive, no charge on the left. Now the next step follows, balancing the number of elements. We have one lead, fine. We have one S, fine. We have 4O, 4O, but here it doesn't work. So how do we have to go on? Oh, yeah, sorry, PPO2. Yeah. So even for the oxygen, it doesn't work. So what do we have to add on the right side for the balancing? Sorry? Oxygen. I don't think so. Why oxygen? Then what is then if you have elementary oxygen, it is a redox reaction as well for the oxygen, but the oxygen is not oxidized and not reduced. We have -2, we have -2, we have -2. And we have -2. So what will be the product on the right? Again? I heard it. Who was it? 6H2O, yes. Yeah, if you calculate now, we have 3, 4, 12H. So 6 times 2 is 12. And we have 4, 8, 10, O. We have 4 and 6, 10, O. Now it's fine. That is what we already learned. In an acidic environment, the balancing of the charges has to be done by protons or H3O plus. In an basic or alkalic environment, you have more OH minus. But here we don't have OH minus, here we have H3O plus, because we have a strong acid here delivering a lot of H3O plus. Well, the overall redox reaction now, we have 2 electrons, okay, that is the reduction. So it's done. Now let's write it. Here I have lead elementary, and I have lead oxide, and I have 2 sulfate on the left side, 2SO4, 2 minus, and I have 4H3O plus on the left side. And then when I read it from the left to the right side, it leads up in lead 2 plus PB sulfide. So we have here on the right 2 of them, 2SO4, 2 minus. So that is the lead sulfate plus 6 water. And from the left to the right, this is the discharging, which works by itself. And if you want to charge it, you have to add power from outside. Then you can force it in the opposite direction, charging. So in the car, well, first of all, you need the electrical power to start the engine. And then you are driving. Are you connecting a normal fossil-driven car to the socket for charging? No. So how does it work? Loud? Yeah, there is. In the engine, of course, you have rotation. And so you can operate a generator, the light machine, we call it light machine, the generator, which is producing electrical power for charging the battery. And even when you need some electrical power for the light, for your radio system, for your window cleaner, whatever, operating with electrical power that's produced as byproduct of the rotation in the engine, and you use it in a generator to produce electrical power. But it's always stored, intermediate in the battery and used out of the battery. The difference in the redox potential in this system, the delta E, is 2.04 volt. When we have one system looking like that, that's the difference in the redox potentials. When you look to a battery, do you know what's the voltage of a normal battery in the car? 12 volt. So how can you get 12 volt? Twelve. I have 2. I need 12. You have just in parallel 6 systems like them. And then you have to think about the Kirchhoff's laws. Do you know about the laws from Mr. Kirchhoff? Yeah, if you have in parallel the system, the voltage is the sum of them. So you have 6 of them, then you have 12.2 volts, something like that. Huh? Yeah, 12.24. Fine with that? So if I will ask you how a battery in a car works, you're fine to describe it. Maybe I ask something else. I ask you, we are now, today we heard in the COP28. Do you know what this is, COP28? Yeah, that's the conference of the parties here worldwide. People from the IPCC, the International Panel for Climate Change, are meeting. And today they had the last day. And they thought about, okay, we have to step out of the fossil world. It's not a hard decision, but they are on the way to the end of fossils. The more and more we step out of this world, the more and more we have to invest in renewable energies. So, well, we know, and we talk about in renewables about it, we have fluctuating production. We have wind and PV mostly. So in the daytime, today not. Here in Germany, no, nothing, because there's no sun, nearly no. So we won't have PV production today, or very less. And wind, here in Bavaria, look to the trees, there is nearly no wind. So even that doesn't work. So we have fluctuation in the production, but you look to our system, we need power, even in the winter, mainly more than in summer, because it's more time dark. So we need a storable form of energy. And one of these storable forms is what? Hydrogen. So, well, when we look to our systems, typically we have hydrogen and we have oxygen. And we have 2 of them, and we ignite it. What happens is we have the formation of water. This is the way how it works by itself. And if you ignite it, there's a big explosion. When you have exactly the ratio 2 to 1, it is a big boom. Or if you operate the system in a controlled way, you can even produce electrical power. And this is done in a fuel cell. We call it fuel cell. Because here we are creating energy in form of electrical power. This is where we can use hydrogen. But now, of course, when we are producing hydrogen out of fossil fuels or whatever, that's not a good idea. The good idea is to say, let's produce green hydrogen, and that is done in an electrolyzer when we operate the system in the opposite direction. That is the electrolysis. In an electrolyzer, we add electrical power coming from wind and photovoltaics or other renewable sources, and we split up water in hydrogen and oxygen, but that needs power. But what is the big advantage? We have now hydrogen, and hydrogen can be stored. Electrical power we can't store. We just can transform it into anything else in a battery, but that's not electrical power. It's a storage in form of chemicals, even in the battery. In the battery, we transform the electrical energy into chemical energy while we are pushing the electrons in a way that we have other systems, but it's a chemical storage. But in the batteries, you might need a lot of lead, a lot of lithium. We won't have it to cover all the energy needs we have. So we need other forms of chemical compounds which can be stored, and that's hydrogen. Because that's a gas, we can put it into a tank and store it from the summer to the winter, and then use it in the wintertime. Or we can even drive a car with hydrogen. We can heat our houses with hydrogen. So hydrogen is the future. Maybe in short term, there will be a lot of challenges because it's not so easy to store, to transport, and we don't have the systems working with hydrogen overall, but it will be the future. Today, we are looking to other countries where we have more trust in the political systems. You know, we have some problems on the world with Russia. Now we have other problems with other countries. So we are looking to partnerships with countries where we have more sun than in Germany. And then it's difficult to transport the electrical power, let's say, from the middle in the equatorial region to Germany. So an idea is to produce hydrogen and then use the hydrogen to transport. But even that might not work. So in the renewable world, the hydrogen is transformed or converted into, for example, methane, in ammonia, or in methanol. For example, that's methane or natural gas, or synthetic natural gas, renewable natural gas, ammonia, or methanol. So you will hear quite a lot in future about those systems, because for natural gas, we know we have the infrastructure. Nowadays, we are importing LNG, which is liquefied natural gas from the United States. We can even use methane produced out of hydrogen and carbon dioxide. Then we have renewable natural gas, liquefied and transported, because that can be transported more easy than the hydrogen gas. Or liquid ammonia. Ammonia can be used as energy source. There are even engines working with ammonia. Or methanol. Here the problem is when you burn it directly, carbon dioxide is produced again, because here we have a carbon containing sources, here no carbon. So maybe we need a technology to convert it in a CO2 and hydrogen, and then use the hydrogen because it's CO2-free technology. So there is a lot of development around these system electrolysis of water, hydrogen production and usage, and related to that, there's really a lot of things ongoing. Any questions on that? No question. That's fine. We're done now with the chapter 4, chemical reactions. We just touched a few very important reactions. We had acid, alkali, we had redox reactions. So these are the most important, and please have a look to them. They are really important. Now we come to one of the next chapters. We have a short view just on metals, which is the 5th chapter now, metals. Yeah, because metals, of course, are a very important material for a lot of industrial processes, production, in a lot of industries. So first of all, let's talk about the physical properties of metals. For example, one is the hardness. If we see or have a look to the alkali metals like lithium, sodium, kalium, first of all, we know they are not stable in nature as elements, as elementary metals, because they are oxidized very easy. In contact with air, automatically lithium ions, sodium ions, potassium ions are formed. But if you cover them with an oil where no oxygen can get into contact, you can handle these metals. And if you take them out, you can cut them with a knife. So they are not very hard. So cuttable with knife. So they are not very hard. Alkali metals are not hard. Others, like, for example, chromium, wolfram, iridium, they are very hard. Very hard metals. So mostly the transition metals are very hard. If we look to our periodic table, you know where they are. Transition metals, which type of orbitals are filled up with electrons? When we talk about transition metals, the D. Here we are the S orbitals, the P orbitals, and in between here the D orbitals. This is the area of transition metals. And we have in here the actinoids and the lanthanoids. Here we fill the F orbitals with electrons. And in the transition area, for example, you have chromium, you have even iridium, platinum, palladium, silver, copper. They are quite hard, and very hard is tungsten. In English, it's not wolfram. In German, it's wolfram. It's tungsten in English. Tungsten is one of the hardest metals we know. Even tantalum is very hard. If you have a broken leg, platinum normally is used to repair it, to stabilize the bones. Because platinum is very noble, so it won't oxidize in your body. It will be stable for years, and it is very hard and stable material as well. Of course, it's expensive, but do you want to have iron in your body and then it's corroding in weeks? Yeah. Do you like to have? Sorry. Oh, titanium is used even, yeah? Titanium or platinum. Titanium is even very expensive. So here we have those. For example, a very hard material which can be coated on surfaces to enlarge the hardness of tools, of mechanical tools, like a drilling tool. Hey, of course, it's very expensive to have it out of platinum or titanium. So there is a technology, we coat iron, a driller out of iron is coated with tungsten carbide. Tungsten carbide is a mixture of two metals, and you can coat the iron with different technologies. In plasma technology, to put that on the surface of the iron, then it's harden it. And this is, we call it VDR. VDR means like diamond. You know, diamond is very, very hard. Carbon in form of diamond. And the tungsten carbide coating is even very hard, like diamond. And we coat material which are more cheap, like iron, with such hard coatings to have a special tool when you have to apply it on other materials for drilling a hole or whatever. The density is another physical property. Here, even very low density, for example, for the lithium. The typical symbol for density is a rho, Greek symbol. The letter for lithium, it's 0.53. What's the unit for density? Yeah, kilogram per cubic meter, or here we have gram per cubic centimeter. Osmium, for example, it is quite hard. Here we have a hardness of 22.48 gram over cubic meter. So there is a big difference between those two elements, and osmium is even in the area of transition metals. So this is a very dense material, so it means it per volume is quite heavy, has a high mass per volume. Iridium as well. Iridium, the density is similar to osmium, 22.5 gram per cubic centimeter. So here, even a big difference. So we divide our metals in light and heavy metals. The light metals, typically, here the density is below 5 gram per cubic centimeter. So is below or equal to 5 gram per cubic centimeter. These metals we call light metals. Aluminium, for example, is a light metal. It's quite light. You can carry it quite easy. The heavy metals, of course, are heavy. And here the density is much above 5 gram per cubic meter. So this is a kind of orientation. The limit 5 is the distinguishing between light and hard metals. Let's go through our different types of metals. First is the alkali metals. Let's talk about them. We already did it. Where can we find them? Of course, they are light, and they are in the first group of the periodic table of elements. You know that the alkali metals, hydrogen, of course, is not a metal, it's a gas, but the others are alkali metals. They are very light, and they are in the first group of PTE. They are light metals. And in nature, they are not occurring as elements, not in elementary form. In nature, not occurring in elementary form. That is what we even discussed quite several times. So the oxidation number is always +1. Because we have one s electron from the s orbital, which can be delivered to any partner, and it will be delivered in most of the cases when possible. And then we have the previous noble gas configuration in the electrons. In nature, they are salt Bildner, part of the salt Bildner. So in nature, they occur as salts. The most common one is the sodium chloride. So the sodium, of course, is the important one, the alkali metal in here, and they are soluble in water normally. So if we have the sodium and we put it in water, it's soluble. What happens? Loud, please. Yes, Na plus and H2 is formed because when you look to the table of redox potential, we have the formation of Na plus and H2. So now please help me to balance this redox system. First of all, sodium oxidation number 0. Here, +1. So we have here from 0, we change to +1. What? That's an oxidation, huh? And what will be reduced? Okay, what's the oxidation number in here? +1, and here 0. So we have H2 and even here 2 of them. So how many sodium do you think are needed? 2 electrons are needed to form H2 gas, because we have 2 hydrogen atoms. So here we have only 1. So how many sodium atoms are needed to create 2 electrons? 2. So we need 2 of them. And if we have 2 of them, we will even have 2 of them here. And what will be the rest? We have now 2 positive charges here. And now we take away a proton here. What results? OH. OH minus. So we have sodium hydroxide and the hydrogen gas is formed. So bubbles will come out of the aqueous solution. We put in the sodium into water. It's not stable in nature. We already said it. But if we have a piece of elementary sodium, we can create it via reduction, but then we need force in that direction. And then we have to store it in a stable environment where no electrons can be delivered from any other partner. Then it stays stable in an oil. No contact to oxygen, no contact to other systems where electrons can be taken. Then it stays. But if we put it in water, automatically hydrogen gas is produced. And this happens with all of the alkali elements. They are not stable in nature. So we won't find them outside in nature as sodium. We find it as any ions, mostly in form of salts. We will go through step by step through even the other metals. But now let's have a break. It's 5 minutes past half. Let's meet again at 10 minutes before 4. Okay, back again. Not too many in the classroom, but we will go on. We started talking about metals, and first of all, we talked about the first group, the alkali metals. Now let's switch to the next one, the alkali earth metals. That's those who are in the second group of the periodic table of elements. We call them the alkali earth metals. And they are in the second group of PTE. What are we knowing already about them? In nature, they are not existing as elements. Similar to the alkali metals, they are not stable. They are reactive. And they are forming carbonates in nature. For example, magnesium carbonate. That's called magnetite or magnetite. We have here the carbon in the magnesium carbonate. What's the oxidation number of carbon in here? Please calculate and then say something, not just talking nonsense. What? +6? +6, why? What is the oxidation number of oxygen? -2. What is the oxidation number of magnesium when we have it in the alkali earth metals? It's always +2. What must be the oxidation number of carbon? +4. +6 is even not possible for carbon. The highest is the group number, so +4 is the highest. It can't be +6, then we will take away the electrons from the noble gas helium. And then it will have 0 electrons, but that doesn't happen. +4 is the max. And we have others like a mixed carbonate out of magnesium carbonate and calcium carbonate. Now, this is a very famous carbonate. It's called dolomite. In the Alps, we have mountains called the Dolomiten. What do you think could be found there? Dolomite. Great. So we find it quite often in nature. Besides the carbonates, we have fluorides. I will add it here on the same side. And the calcium fluoride. We had it already once when we talked about the ionic crystals or the ionic type of bonding. Then we had the calcium fluoride as one of the examples of the AB2 type. If you remember, that's an A B2 type. And these calcium fluoride, this type or these fluoride, the crystal formed is called rutile. So another name for it is rutile. When we have calcium elementary and we put it in water, what happens? So we have calcium elementary and we put it in water. And we know it is not very noble, the calcium. Normally it's not stable in nature. So what will happen to the calcium? It's not stable in form of elementary calcium. So what happens to it? It's not noble. It will be oxidized. So it will form calcium 2+ ions. So here the change is from 0 to +2. That's an oxidation. Again, what will be reduced? Here we have the +1. Even here, hydrogen is formed as a hydrogen gas. So 0. Now, how many electrons are transferred? The oxidation 2 will be delivered. So we have H2. 2 hydrogen atoms or protons will form hydrogen, even 2. So this is fine. But now we have to calculate the charges. What is formed additionally to the hydrogen and the calcium 2+ ions? What do you think? Here we have 2 positive charges. Oh, sorry. Oxygen -2. Did you ever hear about O2- existing singularly? If you take away a proton here, what remains? If you take away a proton from the water, what remains? What? With what charge? So OH-. How many of them are needed to balance this calcium hydroxide? So 2 of them. Now let's calculate the number of elements. We have on the right side 4 hydrogen and 2 oxygen. So how many water molecules are needed on the left side? 2. 1 calcium, 1 calcium, 4 hydrogen, 2, 4 hydrogen, 2 oxygen, 2 times 1, 2 oxygen, fine. And this is an alkali, a calcium hydroxide. So these alkaline earth metals are quite relevant. For the building industry. You have, for example, the calcium carbonate, CoCO3, and we call it chalk. Or the slaked lime. That is the calcium hydroxide. The plaster. That's the calcium sulfate. with two crystal water which are added to the sulfate. Now, each time when we have a dot between two molecules, in this case, when this is water, we call it crystal water. It's more or less a not so strong interaction between the sulfate crystals and the water molecules. Two of them are oriented around them. That's the cluster. So maybe you heard about that in the building industry. It is even relevant when we talk about